Hello everyone, I am Dr. Belmont and today we're going to continue with our general chemistry class course. So let's jump into business. And today what we're going to discuss is the topic of calorimetry of chemical reactions. Okay, usually I type this like Rx, very well. So in chemistry it's very important to measure the energy of a reaction, right? We need to know how much energy a reaction is going to either release, if it's going to be exothermic, or absorbs in the case that it is endothermic, right? So an exothermic reaction is one that is going to give away energy, and the endothermic is the one that needs energy, okay, to happen. Very well. So how are we going to model this? Well, it's pretty simple. Do you remember that we discussed this? That you can have A and that you can have B, and if A has more heat than B, then the heat can go from A to B, or all the way around. For example, if B has more energy and A has less energy, sorry, then the energy will move from A to B. And this system, it's easier to understand, a little bit more complicated to model, but easy to understand because it's an heterogeneous system. Right? That means that I can easily identify which part is B and which part is A. Very well. So the problem with chemical reactions is that usually they are not heterogeneous, right? They are homogeneous. So in this case, we're going to have to do a little bit of changes in our model. So I'm going to write still, right? My transfer energy boxes. But here what I am going to type is the reaction, right? And here what I'm going to type is the solution. And let's talk, for example, for the case of exothermic. So if a reaction is exothermic, that means that it's going to release energy. That means that it's going to give away energy. And how is going to that happen? Well, if it's an exothermic reaction, then the energy will flow from the reaction towards the solution. So I'm going to type down this direction. And what happens if the reaction is endothermic? Well, it's going to need energy. So it has to be what? The opposite way. And if it is the opposite way, that means that the heat will flow from the solution to the reaction. Very well. So let's take, for example, the next reaction. HCl plus NaOH, that is going to give me NaCl plus H2O. This is a very common reaction, right? That we know that is going to happen. And we know, because in the lab we usually measure this reaction pretty easily, that here the change of temperature is going to be what? Positive, meaning that the reaction is exothermic. But what about if I want to erase this and now make the reaction go all the other way around? So let's go to the next page and say, for example, that NaCl plus H2O can give me away NaOH plus HCl. Well, chemically speaking, this reaction can happen. The only thing is that if from acid and base you releases energy, right, then what you need to do from salt to acid and base is that you need to add energy. But theoretically speaking, the reaction can happen on that way. So let's go and clear all of this, and let's continue with the example. So let's retake our model of boxes. So I have my reaction and my solution. And remember that most of this is what? An homogeneous system. So in our reaction, HCl plus NaOH, right? That is going to give me NaCl plus H2O, right? If I want to measure the heat that the reaction is going to give away to the solution, for example, then I also need to make my system what? Homogeneous, right? How? Well, basically, in chemistry, we need to use a media, right, or a solvent to make things homogeneous, and in this case, what we are going to use is water. That means that every single thing that I have in my reaction is going to be aqueous, even the water. Yeah, I know that it sounds a little bit crazy, but you can have water in aqueous media. Actually, that's the idea. Very well. So since the change of energy of temperature, here, it's positive, that means that this reaction is going to be exothermic. So the reaction is going to give away energy to the solution. How are we going to measure that? Well, very simple. We need to remember our definition of heat. And the heat is going to be the same as what? As the specific heat of whatever you want to study times the mass what you want to study times the change of temperature. So let's go. So let's start to model what we want. We want to model the heat of what? Of our reaction. So I type down heat of the reaction. If that is true, then what I need is the specific heat of what? Of the reaction times the mass of what? Of the reaction times what? The change of temperature of the reaction. But look at this. I cannot have by myself only what? The reaction, right? I cannot have alone, just like in the vacuum of space, or well, it would be difficult to have it, HCl plus NaOH and NaCl plus H2O, right? So actually, the reaction is going to be carried out where? In a solution. So what I actually need to measure is the Q of what? Of the solution. And since they are basically very similar, I can say that the Q of the reaction is going to be mostly the Q of the solution. So changing my variables, what I'm going to have is that I will need what? The specific heat, but not of the reaction, but of the solution, times the mass of the solution, times the change of temperature of what? Of the solution. And we actually have this. Now, for example, let's say that I measure the mass of my whole system, right, after the reaction finishes. And I'm going to say that I will have 100 grams, because these I can measure and these I can measure pretty easily, right? I can use a thermometer, measure the temperature, I can use a scale, measure the mass. But what are we going to do with the specific heat of the solution? Very well, so let's go and jump to another page. So I know that the Q of the reaction is mostly going to be the same, the Q of the, let me check to make sure that I'm saying lines, yes, of the solution, and this is going to be the same as the specific heat of the solution times the mass of the solution times the change of temperature of the solution. Very well. So let me check something. Yes, very well. We can measure this, but we have to do something about this, right? It's going to be very difficult to measure for our system HCl plus NaOH, right? That's going to give me NaCl plus H2O, right? The specific heat capacity only for this system. But remember that we're using what? An aqueous media. Sorry. And let's say that I'm going to perform this reaction quite diluted, right? So basically the solution is mostly going to be what? Also the heat of water. And if that is true, do you remember that in our previous example, I made a consideration that the specific heat of steel is going to be mostly the same, the specific heat of iron? Well, I can apply exactly the same criteria for this example. So for the Q of solution, I can use the Q of water, meaning that the C of the solution, if it is what? Diluted, is mostly going to be the C of water. So let's go and continue in another page. Very well. So the Q of the reaction now is going to be defined, right, as the, C of H2O times the mass of the solution times the change of temperature of the reaction. And this is going to be specifically, right now, talking only about HCl plus NaOH. That is going to give me NaCl plus H2O. Perfect. And all of this is going to be diluted in aqueous media. Very well. So imagine that you have your reactor here. You're in the lab. You have NaOH, right? And you start with an initial temperature of 22 Celsius. Then you add HCl. The reaction happens, and what you have at the end is only NaCl plus H2O. And the final temperature for that is going to be, let's say, for example, 28.9, according to an exercise that I found in the book. Very well. So I have what? My change of temperatures, right? I measure the mass of this, and I'm going to say that it's going to be, after the reaction, something about 100 grams, right? And if I go to one of my books and I look for the specific heat capacity of water, we already know this almost by heart, that it's 4.184 joules over grams and Celsius. So let's jump to the next page. And then the Q of the reaction is going to be the C of H2O times the mass of the solution times the change of temperature also of the solution. And just jumping and throwing numbers, what I will have is that if I substitute this number, is going to be 4.184 joules over grams and over Celsius times the mass that I measured, that is going to be 100 grams, and the change of temperature. Remember that the change of temperature is going to be what? Final minus initial, right? So in this case, what I will have is 28.9 minus 22.0, and all of these are Celsius. So let's check the dimensional analysis. Celsius will go with Celsius, grams will go with grams, and since I am looking for heat, the correct unit is joules. So the dimensional analysis tells me that I am doing apparently everything okay. So when you perform the math for this, you will get that 2.9 times 10 to the 3 joules is the amount of energy that from the that was released from the exothermic reaction of HCl plus NaOH to give me NaCl plus H2O. So for this reaction with these conditions, right, what I got was this amount of energy released. And according to Dalton's law, right, multiple proportionalities, if I increase what? The numbers of moles of these reactants, then the energy is going to rise. If I, for example, decrease them, right, then also the energy that I'm going to release is going to be decreased. Very well, I think that it's going to be everything for today. I want to do this video as short as possible, and I will see you later soon. Goodbye.